How do mechanical engineers choose CFD turbulence models? Have you ever wondered how mechanical engineers decide on the right turbulence model when using computational fluid dynamics software? It's a fascinating process that combines science and practical considerations. Let's break it down. Mechanical engineers typically select turbulence models based on the specific characteristics of the flow they are analyzing. They consider factors like accuracy needs, available computational resources, and the nature of the problem at hand. Understanding the strengths and weaknesses of each model is essential for making the right choice. Turbulence is a complex flow phenomenon marked by chaotic and irregular fluid motion. Because simulating all turbulent scales directly is not practical for most engineering tasks, engineers relying on turbulence models to approximate turbulence effects on flow. One common approach is using Reynolds-Averaged Navier-Stokes models. These models average turbulent fluctuations to solve for mean flow properties, making them efficient for engineering applications. Within this category, the k-epsilon model is popular for fully turbulent flows with simple geometries. However, it may not be as accurate near walls or in separated flows. Another option is the Komega model, which excels at capturing effects close to walls and in low Reynolds number flows. It performs well in scenarios with adverse pressure gradients. The shear stress transport Komega model combines the strengths of both Komega and k-epsilon models, improving predictions of flow separation and reattachment. This model is commonly used in aerospace and turbomachinery applications. For more complex flows, engineers might choose the Reynolds stress model. This model solves transport equations for Reynolds stresses, capturing anisotropic turbulence and intricate flow features. While it offers higher accuracy, it also requires more computational power. Large Eddy Simulation is another advanced option. It resolves large turbulent structures directly while modeling smaller scales. Although it provides high fidelity, it demands significant computational resources and is typically reserved for specialized applications, such as combustion or external aerodynamics. When selecting a model, engineers consider the type of flow involved. Internal flows, like those in pipes, may require different models than external flows, such as those around vehicles. The presence of flow features like separation, swirling, or heat transfer also influences the choice of model. Mesh resolution is another critical factor. A fine mesh near walls is necessary for models that resolve near-wall turbulence. Otherwise, engineers may use wall functions. Computational resources play a significant role too. Higher fidelity models, like Large Eddy Simulation or Reynolds stress model, requiring more computing power and time. Lastly, accuracy requirements matter. For preliminary designs, simpler models may suffice. However, detailed analyses often call for more advanced models. In practice, mechanical engineers using computational fluid dynamics software often start with Reynolds-Averaged Navier-Stokes models like shear stress transport Komega. This choice strikes a balance between accuracy and efficiency. They ensure the mesh quality supports the model's assumptions, especially near walls. For complex or novel flow situations, engineers may run multiple models to compare results or opt for advanced models when justified. In summary, mechanical engineers choose turbulence models by evaluating flow physics, computational constraints, and accuracy needs. They select a model that best fits these criteria while ensuring proper mesh and boundary condition setups within the computational fluid dynamics software environment.